He's a swing theorist.
Oh,
Yeah, but apparently he's branching out into other domains.
well, Bentsen is a wonderful.
Yeah,
It's a long way away from here.
it is. We have to drive across the country next week.
Next week.
Yeah, he's supposed to start his postdoc in September 1st. So it's
Well, this will be a nice time. I hope the heat breaks in these.
yeah. Yeah. Last time I checked, it looked like we shouldn't have any like especially bad storms or anything, but you never know in the Midwest. We do have to drive across Kansas.
Well, I usually like to sit in the way back. I think I'm
No, I just need
way front.
Right, use it, try this first into the waters. Others are pros. All right.
You're live.
All right, great.
Live and in color.
We'll be ready to go in about 5 minutes. So someone can move remotely. We are streaming, actually. So we're streaming to YouTube. Thanks.
To New Zealand, is that what you
To you, just to YouTube.
To your audience.
Not.
We
Oh,
advertised it. We may or may not.
actually, there are
said?
two.
Brothers might watch, you know.
There are two people watching right now.
Are there?
Hello, two people.
Does it say who they are?
No.
I kind of doubt Bradley's probably working.
She's live streaming.
Jeffrey's camping. Well, that's cool. It's on YouTube? I'll send a text to.
Yeah, the link is in the Facebook invite.
So I've been trying to figure out if there's a way that I'll actually get access from my
Yeah.
If you want to use this, he hasn't written this in a while. He'll probably eat afterwards.
Just mine.
So then, it boils down to count. So you count how many
Oh, hang on, I got my husband's here too, but. Got it, yeah. Get back here. Their group has grown. We have, yeah, it's always fluctuates a bit in the summer, they sit on undergraduate. Yeah, so, hey, good, how are you? Ready, this is your first, it's like your first child. Very exciting. That's great, yeah. Don't go, just wait, then maybe afterwards, the tables and the chairs, this would be really Jeffrey says he's one of his.
Do you want to say hi to Jeff?
Hi, Jeffrey. Glad to watch you. I did. It's my note. Jeffrey's watching she said there's two members. It's my Jeffrey
Yes.
It turns out I can send you and the older kids are just and so the exact one is easier to keep.
All right, I have the great pleasure of introducing Greg Bentsen for today's thesis defense. Greg is somebody who actually arrived at Stanford intending to be a theorist, but he has, as some of you may know, a very broadly curious, inquisitive mind, and thought he might just take a small detour to trying out what experimental physics is like. And being Greg, he did this in the boldest possible way, joining a new faculty member with practically an empty lab, just one other graduate student building up a very technically demanding, complicated atomic physics experiment. And along the way, though, he sort of never lost his passion for theory. And this led to a lot of actually really remarkable collaborations with fields ranging from condensed matter, but also to quantum gravity, which allowed Greg really actually by spanning these different worlds to really pioneer actually a new field in terms of what's possible in experimental research and connecting to some very fundamental ideas in physics. And so I think you'll hear more about that today from Greg, and I just want to thank him for an amazing few years here at Stanford, and look forward to hearing about your thoughts.
Thank you. Thank you very much for that very kind introduction. I have to say it's been a pleasure working in Monica's lab, largely because she has let us sort of pursue our interests wherever they may be. So one of the things that got me interested in physics way back when I was in college was actually the open problem of quantum gravity. And as Monica mentioned, that has still been one of my interests. So I thought it might be appropriate to start my thesis defense with that theme. So the problem of combining gravity with quantum mechanics is a very, very old problem. It's a very difficult problem. One proposed solution to this is that the smooth space-time that governs gravitational physics is actually made up of microscopic quantum degrees of freedom. This is colloquially referred to as it from qubit. This is very similar to the sort of thing that happens if you pick up a glass of water. The water in the glass looks like a smooth, continuous fluid, and yet we all know that it's made out of discrete molecules. So suppose this were true. Suppose that gravity is actually made out of these little microscopic degrees of freedom. I have control over some quantum degrees of freedom in my laboratory upstairs. Sorry, not my laboratory. we have some microscopic degrees of freedom available in our laboratory upstairs. And if this proposal that quantum gravity is made out of little microscopic degrees of freedom, it stands to reason that I should be able to make these guys interact in such a way that I simulate some gravity. Or even more extremely, maybe I could build a artificial black hole in the laboratory. Now, no one knows how to do this. I don't know how to do this. But we can make some progress on this by asking a bit more modest questions. So suppose that someone approaches you and hands you a piece of quantum hardware and claims that this quantum hardware has a black hole, an artificial black hole. How would you know? How would they convince you whether or not there's a black hole on it? And one signature that you could look for is this phenomenon called fast scrambling, which is going to be the primary topic of my talk today. And the fast scrambling describes the process of rapid information spreading and rapid information processing in a quantum system. In fact, black holes do this so well that they're conjectured to be the fastest information processors in nature. So if somebody hands you this piece of quantum hardware, the first thing you might want to test for is, well, how quickly does information spread on it? And if it doesn't spread at this limit, well, you know that there must not be a black hole. So in this talk today, I'm going to be talking mostly about this process of fast scrambling. And I'm going to be talking about both experimental and theoretical work towards implementing fast scrambling on real quantum hardware up in the lab. So this has I have two motivations here. One is if we can actually implement this maximal information processing in the laboratory, maybe we can leverage that to do some interesting information processing task. And then with a long view towards simulating quantum gravity, maybe if we actually built a black hole in the laboratory one day, we could maybe learn something about the puzzles of information as it falls into black holes. Okay, so those are some very broad motivations. Let me start, though, by defining what fast scrambling actually is. And just for your, as Monica mentioned, I've had a very fun time sort of bouncing back and forth between experiment and theory. And so just to keep things straight, I'm going to give you these little indicators here. So the little blue TH means theory work, which is either pencil and paper or numerical calculations. And then the red EX here stands for experimental work, where I'm actually turning on lasers and driving atoms and those sorts of things, working with my hands in the actual laboratory. Okay, so let's start with this. Let me actually define what fast scrambling is. So scrambling is the rapid spreading of information in quantum systems. And I mentioned earlier that black holes do this very well, but those are very esoteric and abstract. So let's give a bit more of a concrete example. Suppose I just have a beaker of water and I drop a drop of dye in there. And pay attention here, this is going to be purple. That color purple is going to kind of be throughout the top here. If I drop this drop of purple dye, not surprisingly, this drop of dye is going to spread throughout this beaker of water. And this is the picture that I have in the back of my mind, and I want to encourage you to put in the back of your minds as you think about scrambling. So the process of having some bit of information that's very localized, and then it subsequently spreads throughout the system. Now, we're not talking about water and beakers here, we're talking about quantum degrees of freedom. So let me introduce kind of some notation that I'll be using throughout the talk. First of all, each of these red dots is going to refer to a quantum bit or degree of freedom. And this could be any number of things. For the first part of the talk, I'll keep it very abstract. So these things could be electrons, they could be atoms, they could be spins, anything, any finite Hilbert space size dimension degree of freedom. And I'm going to label those by indices I and J. And then this system, any quantum system, if it's going to do anything interesting, these quantum degrees of freedom are going to interact with one another. And so I'm going to draw the interactions between quantum degrees of freedom using these black lines. So in this particular instance here, I've got a two-dimensional lattice. What that means is that the degrees of freedom only talk to their nearest neighbors. So this guy up here is only talking to this guy, and this is only talking to this guy. We're going to see, though, that you can engineer some very interesting interaction structures that are not so simple, that are not just these two lattices. So to get back to the idea of scrambling, though, suppose I take my purple dye and I insert some information onto my quantum system. If this quantum system scrambles due to the interactions between degrees of freedom, this information will eventually spread throughout the system. It's very similar to the way in which this dye spreads throughout the beaker of water. Another analogy that I like to keep in mind, and this actually gets at the heart of what information scrambling really is suppose I put a book down on one of these atoms. If the system scrambles, I can think of that almost as if the system has torn up that book into little pieces and spread the pages around the quantum system. What that means is that in order to recover any of the information in that book, we need to go around to all of the different sites and recover that information, meaning that I would have to have access to the entire system. So what the takeaway here is that scrambling refers to the process where I used to have localized information up here in that book, and it is now been dispersed throughout the entire system, such that it is inaccessible to local Now, the experts in the room here will recognize that this is a very classical process of scrambling, and what I'm really talking about here is the growth of entanglement. But I will throw that under the rug for now, and I'd be happy to talk about it. Okay, so that's the process of scrambling in an intuitive sense. One important result that was discovered about 10 years ago now is something called the fast scrambling conjecture. And this was conjectured coming out of some really interesting thought experiments having to do with black hole information. The fast scrambling conjecture is very simple to state. It states that this process of information scrambling cannot happen instantaneously. So in particular, if you have n quantum degrees of freedom here, the minimum time it will take you to scramble information always has to be larger than the logarithm of the number of sites. And just to put that in very stark visual terms here, as you make your system bigger, it's always going to take you a little bit longer to scramble. But this is actually very special. This is actually a really fast, giving away the name already. It's a very fast scrambler. Most quantum information systems will not scramble this quickly, if they scramble at all. And so these systems right here that actually saturate this bound are known as fast scramblers. And they're colloquially referred to as nature's fastest information processors. So these guys, there's this bound that you can't scramble faster than a certain rate. And the special property about these quantum systems is that they run right up against that bound. And they scramble information at the fastest rate possible. So one question, or a couple of questions we can ask are, what makes these systems so special? What are the minimal ingredients that you have to use to build one of these special fast information processors? And then using that information, can you build one of these in the laboratory? Okay, so that's what I'm going to talk about next, is the minimal ingredients for fast scrambling. What do you need? It will turn out that actually you only need two distinct ingredients to get fast scrambling. So let me motivate this a little bit by talking more about how the spread of information depends on the interaction structure of your quantum system. So for instance, if I imagine I have a quantum system in my laboratory and I chop it in half, so there are no interactions between these two regions, it's fairly obvious that the information spreading is never going to spread over here, just because the systems are disconnected. So this is already illustrating in a very simple way that the connectivity of my graph determines how well and to what extent information is scrambled. Similarly, if I put a single interaction between these two sides, this creates sort of a bottleneck. So information can only spread very slowly between the two sides. These are can be captured in a notion of distance along the graph. And I'm going to introduce this little guy called Dij, which is called the graph distance. So if I label my two sites by I and j here, Dij is just the number of links I have to hop over in order to get from site I to site j. That's called the graph distance. There's another sort of more global measure of distance called the graph diameter. And this is the longest such distance. So if I take all pairs of sites and I look at what's the longest one, that will give me the graph diameter. It sort of tells you how big, how spread out the system is overall. This system in particular, because it has this bottleneck, has a very large diameter, relatively. This kind of a graph, by contrast, this is a random sparse graph. And by contrast, this has lots of non-local connections that are connected to all these different quantities of freedom. And therefore, it actually has a very small graph diameter. And therefore, we expect scrambling to happen very quickly. So the point I want to make here is that the interaction structure of the graph, in particular the graph diameter, plays a big role in how quickly information can spread throughout the system, which makes intuitive sense. Okay, let's make this a little more formal though, because I need to use some of this technology to motivate further work here. So in order to measure, I've argued that we have this purple blob and it's spreading around, but let's actually make this a little bit more formal and more technical. What we're going to do is actually measure commutators. And for the experts in the room, the formal name for these is the out-of-time order correlator, or OTOC. For now, I'm just going to call them commutators. So what I'm going to do is on this graph of quantum degrees of freedom, I'm going to apply two operators, operator A and operator B at different sites. And because they're at different sites, they initially commute. Well, what's going to happen is that under time evolution, operator A is going to grow. And again, for the experts here, this is just a Heisenberg evolution of the operator It's going to spread throughout the system slowly until eventually this purple blob meets the green blob, and these two operators now fail to commute. So the time-evolved operator A of t now fails to commute with B as a result of the spreading. So let me repeat that again. So at early times, when A is localized on its side and B is localized on its side, these guys commute, C is 0. As this guy spreads along, we now see that C starts to grow. So this provides a really sharp diagnostic for how to measure information spreading in quantum systems, because all we have to do is go into the lab and actually measure this commutator. And that will immediately, as soon as we see that commutator grow, we can say, oh, interesting, information has spread from here to there. So the takeaway here is commutators measure information spread. So again, if you want to do this in the lab, we actually showed in a paper a few years ago with Brian Swingle, Patrick, and Monica, that these commutators are accessible in real experience. And in fact, what was really exciting is that shortly after a bunch of groups actually implemented these in the lab, were variants of this protocol. So these commutators really are experimentally accessible, and you can just work with them and see how much information is growing. Okay, so these commutators contain information about how information is spreading. That's not the only thing that they contain. They also contain information about classical chaos, which is a really interesting connection. I apologize here, this is going to get a little technical. What we're going to do here is we're going to replace A and B. Suppose A and B are two canonically conjugated variables. If you do a semi-classical expansion in H bar, take H bar to 0, the leading term you get out here is a sensitivity to initial conditions. So what this means is that the position of, let me just put out this picture here. If you're looking at a chaotic system and you perturb it by just a little amount, if the system is chaotic, the sensitivity to initial conditions will grow exponentially with the Lyapunov exponent given by lambda. And this is something that you probably have heard of before. This is called the butterfly effect in classical chaos. So these commutators actually also contain information about classical chaos. Now, these two ingredients together, the fact that these commutators contain information about the connectivity of the graph and they also contain information about chaos, suggests that actually these are the two conditions that you need to meet in order to get fast scrambling. So to show that, what you can do is you can bound this commutator by something called a Lieb-Robinson bound. And this is something that has been done by many authors in various forms over the years. And we can see already here, so we can see already that this red region is the Lieb-Robinson bound. And what it says is this commutator, as it grows, it can never enter this red region. So it can grow really slowly and wobble down here. It can grow really fast, but it can only grow up to that bound. And this bound actually contains two different ingredients in it, the two different ingredients that I was just telling you about. This bound contains information about chaos, so it contains the Lyapunov exponent. And it also contains this D, which is the graph diameter, which I introduced earlier. And that tells you something about the connectivity. Now, for the experts, we actually proved recently in a paper with Yingfei Gu and Andy Lucas that we could actually show that this bound was a little sharper, and we could show that this was explicitly related to the adjacency matrix of the interaction graph, including, so this A here is the adjacency matrix, and the D is the degree matrix. So this is really nice, and this follows from. But for now, I'm going to be interested only in the simpler graph. So suppose I look at this bound, and I look at this for a two-dimensional lattice system, as I was introducing before. Now, the graph diameter of this system is large, quote unquote large. It goes like the square root of n, which is much larger than the logarithm of n. What that means is, let me orient you to this diagram here. What we're trying to do is build a fast scrambler. And so what I need C to do is I need it to grow rapidly enough to hit this point where it has hit a value of 1 at a time t star equals log n, which is the defining feature of the fast scrambler. The point about this bound is that because this bound, this red line, has pushed the possibilities away from hitting that fast scrambling point. So no matter what we do, whether the system is not chaotic, whatever it does, there's no way it can be a fast scrambler. So the takeaway here is we were wondering if this was going to scramble. Nope, it's not going to scramble. And the reason it doesn't is that local interactions, the fact that this has a large graph diameter, prevents the system from fast scrambling. Okay, so now let's look at another graph. This is our other more highly connected graph. This graph has a much smaller graph diameter. This has a diameter that goes like the logarithm of n. And so if I redraw this again, my Lieb-Robinson bound now has been pushed up. So now this fast scrambling point is actually kind of within reach. But now it depends on whether or not the system is chaotic or not. These C's, if the system is not chaotic, we expect them to grow polynomially, which is schematically what I've drawn here. So if the system is not chaotic, it still won't be a fast scrambler. It's only if you have a small graph diameter and you have chaos that it will be that fast scrambler. So in this case, we see that this type of an interaction graph, so long as it has chaotic dynamics, we expect it to be a fast scrambler. So I'm going to motivate the remainder of my talk by discussing these two ingredients and how we can implement these two ingredients in the lab. So if you want to build a fast scrambler, you need first non-local interactions, meaning a graph of interactions where the diameter grows logarithmically with the system size. And second of all, you need chaos. So those are the minimal ingredients for fast scrambling. Let's see if we can actually implement some of those ingredients in a real laboratory situation. So chaos itself is actually relatively easy to implement. In fact, most systems around us are naturally chaotic. So that's not a big deal to implement. The harder thing is going to be doing non-local interactions, these small graph diameters. The reason for that, solid state material, like graphene, or if you have some atoms hopping in and out of the lattice, these types of systems inherently rely on local interactions. So this atom right here is only talking to its nearest neighbors, maybe its next nearest neighbors. And so we get these graphs like this that we've seen before, where the graph diameter is very large, and we already know that fast scrambling does not happen. By contrast, a system like an optical cavity naturally generates non-local interactions because we use freedom. And so instead of a local graph like this one, we get this all-to-all connected graph. And so we do expect this to be able to support fast scrambling in certain cases. Okay, so let me show you how this system generates non-local interactions. I've just advertised that it does, but it's fairly simple to see how. So first of all, what do I even mean by an optical cavity? I haven't even told you what experiment we're running upstairs. What we have up in the lab is just a pair of mirrors. You can think of it as just like your bathroom mirrors, except with a very high reflectivity. And that supports a cavity mode where photons can bounce back and forth between mirrors. What we do is we load a bunch of atoms into the mode of that cavity. And because they're coupled to the mode, they can emit photons and reabsorb photons from that mode. In doing so, they can actually send photons to each other. It's almost like calling each other on a cell phone network, so they can communicate with each other. Now, the atoms that we use in our lab are rubidium-87, and in particular, the states I want to focus on here are the F=1 hyperfine ground state manifold. And this ground state manifold contains three different states, plus MF equals +1, -1, 0. And I'm going to refer to those using these little cartoon graphics here, full circle, half circle, empty circle. For the moment, I'm going to ask you just to forget about MF equals 0, just to keep things simple. And I'm also going to delete all the other atoms. Let's just say we have 2. And these guys are in spin down and spin up, or 0, -1 and 1. What I'm going to do now is drive the system with some drive lights, meaning I'm just going to shoot some laser light into the cavity from the end. And what that does is it introduces this 4-photon coupling between the pairs of atoms. So let's start over here on this side. I start with my atoms and spin down and spin up. What happens is that one of the atoms picks up a photon from this drive field. I apologize, the colors should match. This picks up a photon from the drive field, emits a photon into the cavity. That photon bounces around for a while. Then it gets picked up by the second atom and re-emitted into the drive field. So these two atoms have therefore exchanged a photon, and they therefore flip their spins. So formally, you can write this down as an S+S- type Hamiltonian. And the neat thing about this is that in the very ideal case, you get interactions like this not just for a pair of atoms, but for every pair of So every single pair of atoms I can think of in a cavity, I can interpret. And that's reflected in the fact that the sum down here is a sum over all pairs of ions. And this is exactly what I mean by non-local interactions. So if I were to draw this interaction in a graph, it would be that complete graph. Okay, great. So we get a graph of interactions that look like this, and I hope I've convinced you so far that optical cavities really are naturally suited for generating these types of interactions. Great. These have all been cartoon pictures, but can we actually demonstrate this in the lab? That's the hard part, right? So I'm going to show you that we have. So let me provide you with a little bit of an introduction to our experimental apparatus. First, let me get So this is a top-down view of our experiment. And to sort of introduce you to it, I'm going to take you through the life of an atom in this experimental setup. So we start out with a rubidium source, a solid rubidium source in a vacuum chamber. Those just from vapor pressure enter the 2D MOT, and there we use, I haven't introduced new terms here, this is a magneto-optical trap. And that's a standard method for trapping and cooling atoms. So we trap them there that form sort of a cigar-shaped ensemble. And those atoms then flow out into the main science chamber where they are trapped by a second 3D magneto-optical trap. Okay, so now, and that 3D optical magneto-optical trap is at the center of the cavity mode. What we do then is we turn on a very deep 1560 nanometer optical lattice that forms a standing wave mode inside the cavity. And then we turn off the MOT and the atoms are just trapped inside this standing wave mode. So what I've done here is I've drawn the 1560 mode as these blue wedges here, and then the red spots here are the actual atoms that are trapped in some of these antimodes. One thing I do want to point out is that currently, in each lattice site, we actually have multiple atoms. So we have around 100 atoms per lattice site. So you should think of these instead of just being one little spin, there are a bunch of them. And just to give you a sense for the technical difficulty of this was basically building this mechanical cavity, was a significant portion of Emily's PhD work, and getting the laser locks to this thing is a significant portion of my PhD. So it's nice to draw this like cute little picture, but it's a challenging technical experiment. So here's an actual image. I apologize, that's actually not very good on the screen. Here's an actual image of our experiment, and you can see on the left side and the right side, these are our two cavity mirrors, and they're separated by 5 centimeters from each other. And if we had atoms loaded in the center, you would see a little red ball. And for the experts in cavity QED, here are some relevant parameters. The few I want to point out are the single atom cooperativity is 7.5 currently. We use about 10 to the 5 atoms. And we're working, the way we get our cooperativity so high is we work in a near concentric regime. So we have a very small list. What's the temperature? The temperature is about 20 megahertz in terms of the lattice, so that's roughly 100. Right, so I have my atoms in my lattice now. And now what I want to do is turn on some dried light and cause them to interact with each other and do some interesting physics. Once they've done all this interesting physics, though, how do I actually extract information out? We have two main ways of extracting information out of the system. One is to look at, remember, I'm driving the cavity from the side, and some of that light causes the atoms to interact, and then some of it leaks out through the other side of the mirrors. We can actually observe that on a photodiode, and that gives us some information about the internal states of the atoms. The reason for that is that the atoms themselves act like a state-dependent refractive index in the cavity, which means that the cavity resonance shifts depending on what state the atoms are in. So here in green, we can look at the transmission out of the cavity, and in green, we have the cavity transmission with no atoms. And then it gets shifted left or right depending on what state the atoms are in. So this is one nice way we can get information out. Unfortunately, it's only useful for getting collected information out. So we can tell how many atoms are in one state or the other. We can't tell which ones. And specifically for looking, if we're interested in looking at this information spreading through a graph, we can't just say, well, how many atoms are up and how many are down. We need to know which ones and how much the information is spread from here to there. So we need local information here. And so what we've done is we've borrowed some technology from quantum gas microscopy, and we've inserted an objective lens under the atomic ensemble, and we image fluorescence light from the atoms onto the CCD camera. And that gives us information, spatial information that looks just like this. And so you can, well, I'll break this down a bit. Just to note here, the objective lens has a numerical aperture of about 0.5, which isn't quite up to the standards of the quantum gas microscopy. But that's good news for us because it means that there's still room to push on this. So we get images like this out of the system. And remember that my atoms I'm working with are F equals 1. We have our 3 states. And these 3 blobs right here are exactly those 3 states. The fact that they're out of order is just a technicality, technical details that don't really matter. What we do, though, is we take a region of interest from this and pluck it out. And to orient you, you can think of the atoms. This is the picture you should have in mind. The cavity mirrors are on either side, and the atoms are lying along the axis here. So what we do then is we actually sum over the vertical direction, and we get a horizontal line of pixels that tells us both state and spatial information about the atoms. And then we can do this experiment many, many times, and we can stack those horizontal rows of pixels on top of each other and form images like this. So you can see here in this image that we have some interesting spatial pattern of the atoms. So we have some spatial information. And again, here we're going to be looking at images like this frequently. So along the cavity axis here, this position X is along this cavity axis, and time will be running downwards. So I'm going to start at time t equals 0 up here, and then turn on the dynamics and we get that. So what's really nice about this system is that we get both state sensitive and spatial information about the atoms. Okay, so that's sort of a whirlwind tour of what this machine is and how it works. Let's see if we can actually see normal interactions. So kind of back to the main thrust. So we have this Hamiltonian here, this all-to-all S plus S minus Hamiltonian. And what we're going to do to see this dynamics is we're going to initialize them all and spin down first, so -1. And then we're going to use a local Raman pulse to create some spin excitations in one region of the cloud. Then we're going to turn on this drive light, and that will generate this Hamiltonian dynamics. And what we expect to happen is that spin excitations in this region will hop out into other regions. And because this is an all-to-all model, we expect that this hopping won't just happen locally nearby. It'll happen to regions that are completely separated. And that's exactly what we see in experimental data. So this is a series of images constructed by the algorithm I talked about earlier. So we're taking images from this camera and forming a ROI and then compressing them along the vertical direction and then stacking a bunch of them in a row. So to orient you here, what's going on is that I start out with my spin excitations up here in this region that I created. And then I turn on the dynamics, and what happens first is that these guys hop immediately over to this region. And this immediately tells us that we have non-local interactions happening like that. Because, by contrast, what we would expect for a local model would be some ballistic diffusive spread like this, if the interactions were only allowed to hop by single sites. And let me actually go back here. So this is experimental data here. We can see that this region hops to this region B over here and over here, before at the end this is taken over by dissipative effects. Now we can also simulate this in numerics using the mean field model, and we see very similar both qualitative and quantitative agreement. So what this tells us is that we understand the Hamiltonian that's actually occurring in our system, and we can plug it into a computer and get the same results. So the fact that this hopping happens non-locally is our first indication that indeed we do have non-local interactions happening in the cavity. Now that's not all we can do. The images I just showed you were spin exchange interactions. The next thing I'm going to show you is a slight variation on it called spin mixing, and it will show again that we have non-local interactions in the cavities. So again, remember I have 3 levels in my atom. And this time I'm going to ask you to pay special attention to the n=0 atoms. We're actually going to prepare our atoms in n=0. Now what happens is if you prepare your atoms in 0, and you apply this Hamiltonian, what's going to happen is that pairs of these are going to, in a correlated way, create pairs of spin excitations in +1 and -1. And you can sort of think about this if you're coming from more of a high energy background. You can think of this 0 as forming sort of the vacuum state, and then you've got your particle here and your antiparticle here, sort of creating a pair of particles out of the vacuum. So we can do this in the experiment, and what I'm doing here is we're going to prepare all of our atoms at MF equals 0, run this for a fixed amount of time, and do this experiment many times over. So these are different repetitions of the same experiment. And you see here that on some repetitions, we see that as soon as this, we see that atoms want to get out of this region here. And as soon as they get out of there, they hop over to the left or to the right. So the key takeaway here is that all three of these images are highly correlated. So every time you see atoms missing from MF equals 0, you see that they popped over to MF1. So a little cartoon picture here, I should imagine my atoms starting out in this state, and then they popped over in a correlated way to the left and the right. So both of these together show evidence that we have non-local interactions happening in the cavity, all-to-all non-local interactions. And the next question is, great, we have non-local interactions. We need the second ingredient, but we need chaos as well. And I said, oh, that should be easy, no big deal. Turns out that's wrong. This system turns out to be integrable, which is interesting in its own right. So simple forms of this model have been known to be integrable for a long time. It turns out that even, so this, again, for the experts here, this is a model that has no disorder in it. It assumes that all atoms have been equally coupled to a single cavity group. Even if you make that coupling disordered, this is still, it turns out to still be integrable. Okay, but I haven't explained what integrable means. What integrable means is, instead of this picture that I gave you earlier, where the drop of dye spreads throughout the entire system, if your system is integrable, that doesn't happen. You sort of drop the dye in and it gets stuck. It doesn't go anywhere. You can sort of intuitively see that if you want information to rapidly spread throughout the system, an integrable system is just not going to do it. So this cannot be. A more formal way of saying the same thing is that we can find an extensive set of commuting local operators that all commute. So we have some conservation laws that prevent exponential Leon numbers. Again, we come to the same conclusion that this cannot spread. Now, if you'll permit me just a slight detour from my main thrust here, this model turned out to be really interesting. If anyone is interested, I can walk you through this phase diagram. I just want to flash this up and say that particular model actually has a lot of interesting, rich dynamical behavior that we still don't fully understand. It doesn't really have anything to do with fast scrambling, but it shows some signatures of integrability that are new and poorly understood still. So there's a lot of richness here that we have to understand yet. And some of that is explored in this paper that a couple months ago. Okay, but let's get back to the main point of the talk here, which is fast scrambling. We found that the simplest model in the optical cavity does exhibit non-local interactions, but it does not have chaos. Now, I should point out here that this is for a single mode cavity, and so people like Ben would not have this problem. They have multiple disordered interactions that they can control. But the simplest form of the model in the single mode cavity is not chaotic. So we have to go one step further. So what I'm going to talk about next is a really interesting proposal for doing the types of graphs that I showed you earlier had these very interesting exotic coupling patterns. And I'm going to show you a proposal for doing models that look more like that in the cavity. So I just argued that the simplest model doesn't have chaos, and maybe the reason why is that this simple model actually has too much structure. So remember the graph of interactions for this is an all-to-all. So it looks like this. And it looks very nice and symmetrical. Okay? If we want to add chaos to the system, maybe what we want to do is to introduce some randomness. So we want to maybe pluck out some of those couplings. Try taking some edges away. But one thing that we have to do to make sure that this still can be a fast scrambler, though, is we have to make sure that it doesn't get too big of a graph. Right? For instance, if we were to take away too many of these coupling degrees, coupling edges, we would actually disconnect the system and we wouldn't be able to scramble at all. Right? So we can't take away too many. Now, let me just suggest, because I do know the answer, let me suggest that we study these couplings only when the distance between sites is separated by a power of 2. kind of a weird rule. So for instance here, these guys are nearest neighbors. They're separated by a distance of 1. 1 is a power of 2. 2 is 0. They're connected. This guy and this guy are separated by 2. 2 is another power of 2. These guys are connected by an edge, 0 to 3, because 3 is not a power of 2. So we've plucked that coupling edge out of the graph. But then we also include edge number 4, because 4 is a power of 2. So this graph, you can easily see by inspection that the diameter of this graph grows like logarithm of base 2 of the size of the graph. If I just follow this pattern and make bigger and bigger graphs, this has a logarithm graph diameter, so that's good, non-local. And then in addition, we can look at some easy signatures of chaos in the system. So for instance, we can look at level statistics in the spin 1/2 version of this for small system sizes. And we see that this follows Wigner-Dyson statistics, and therefore it should be chaotic. More directly, we can compute in a semi-classical expansion, we can compute semi-classical versions of the commutator that I mentioned earlier. And these show direct evidence of Lyapunov growth. So in the classical version of this, we see classical chaos. So we have some pretty positive indications that this thing is both, well, we know it's non-local because of its graph, and then we have some pretty positive indications that it's also chaotic. So it looks like this graph might meet our 2 necessary conditions for fast scrambling. Even more so, though, we can actually just directly ask, like, hey, do you fast scramble? Are you a fast scrambler? And what we can do is we can run some semi-classical numerics on this, where we treat each spin as a very large degree of freedom, with a large length. And this allows us to go up to very big system sizes. And if we compute the classical scrambling time in this model, we find that as a function of system size, it obeys this very nice logarithmic growth, just like we'd expect for a fast scrambler. So that's great. But of course, we're not just interested in semi-classical or classical fast scrambling, we're really interested in quantum fast scrambling. So we worked with some collaborators at Strathclyde and Andrew Daly's group, who did some matrix product state simulations of the system for S = 1/2. And they showed that these commutators, these OTOTs, grow in a way that is consistent with fast scrambling. And this is all in this recent paper. So this is nice. So it looks like this is probably a fast scrambler, most likely. So it looks like it meets the 2 criteria that we need for a fast scrambler. If we look at some basic diagnostic tests of this, it looks like a fast scrambler. The last question, though, is this is some crazy model. Do you think I can actually do this in the laboratory? It turns out that yes, I think we can. So this was actually, we thought we had discovered this implementation of this proposal, but it actually turns out we were a couple of years too late. But so this is was originally proposed by Hung and Serac in 2016. But so let me show you how this works. This is really cool. So remember this 4-photon scheme that I showed you toward the beginning of the talk. This is how pairs of atoms talk to each other. So I'm going to have my 2 atoms sit here and here. And if I drive the system, as usual, I get interactions by this 4-photon scheme. What I'm going to do now is add an extra element. So I'm going to add a magnetic field gradient to the system. So that's just a magnetic field that changes depending on where you are. And because these Zeeman levels are magnetically sensitive, what that means is that this atom over here, its energy levels can be shifted depending on its position. And that actually shuts off the interactions. This 4-photon process is no longer lessened. So it shuts off the interaction. But then what I can do is reintroduce an interaction by driving the system with a pair of frequencies at the same time, such that the difference in frequencies makes this resonant again. So what I do is I pick the frequency of the second wave, such that it puts this little transition back on resonance again. And I like to think of this almost like I'm playing a piano. So what I'm doing is I'm putting in 2 different frequencies of light in the cavity. That's like me pushing 2 keys on a keyboard. And that specifically isolates, hey, you and you guys are going to interact. Now, if I have a piano, I can play any keys I want, right? I can play the C and D keys and thereby get nearest neighbor interactions. I could also play the C and E keys, which are separated by 2 sites, and here I get next to nearest neighbor interactions. Or I could do C and G and get 4th neighbor interactions. Or, of course, if I have a piano, I can play not just 2 notes, I can play a whole chord. And that's how we get this full power of 2 interactions. So the nice thing about this is that the only thing you need to do in order to determine the couplings between degrees of freedom is modulate your drive field. So you need to have it be a cone of frequencies where the frequencies determine which atoms are coupled and the strengths determine the relative strength of these couplings. So that's really nice. Now we actually have already seen some evidence towards this. We're not up in this very fancy model where we have 1, 2, and 4 and all sorts of crazy couplings. But we do have some evidence that this basic scheme does work in the cavity. So what we've done is we've initialized all of our atoms in MF equals 0. And remember the spin exchange interaction, or sorry, spin mixing interaction I mentioned earlier, where the two atoms would hop out to the sidelines. That's what we're going to do again, but in a distance-dependent way. And we're going to turn on our drive light at 2 different frequencies. And then because of the magnetic field gradient, this pair creation process is only going to happen at a particular distance in the cloud. So we're going to see these pairs pop, or pairs being created at a particular distance. And when we look at the data here, this is a compressed form of this. What I'm looking at here is a correlation plot between the populations of +1 and -1. Now, if everything were being created uniformly across the cloud, I would just see this straight line through the middle. But because the distances because pairs are being created at a correlated distance in +1 and -1, I see these blobs out here. And so the distance here between these blobs tells us exactly, it ought to, and it does match the frequency difference. So this is great. This shows us some basic evidence. So this is still very early days here, but this shows us some basic evidence that this coupling scheme is feasible in the lab. So that's really exciting. So it looks like we have everything we need here. We have the 2 major ingredients we need for a fast scrambler, and we can do it in the laboratory. So that's really cool. The next thing I want to tell you about, though, is back more to theory. So this graph of interactions doesn't just do fast scrambling. It's also got some really interesting emergent geometry going on in the background. So I mentioned before that I can play this keyboard, piano keys. And of course, if I'm playing a piano, I can play some notes more strongly than others. And what this does is it changes the relative strength of the interactions between atoms. So in particular, if I play the nearest neighbor interaction keys more strongly than the furthest neighbor interactions, then I get a graph that looks like this, where I've sort of faded out the long range interactions. And so this almost looks like a nearest neighbor solution. By contrast, though, I can go the opposite direction, and I can engineer a furthest neighbor model, where I have the keys that are being played far away really strongly. And it turns out, actually, that underneath these 2 spin models is 2 different kinds of emergent geometries. So not surprisingly, up here in the nearest neighbor spin chain, this is described by just the regular real numbers, where 0 is right next to 1, and 1 is right next to 2. Nothing surprising. But in the furthest neighbor model, actually, the low energy physics looks like it might actually be described by this Bruhat-Hitz tree, which actually comes in from holography. Now, that's all very fancy and nice, but really all I mean here is that all we have to do is rearrange our spin sites in order to get this new geometry. So what we do here is we take the bit representation of each of these site numbers. So here, let's take number 3. So 3 has bit representation 0, 1, 1. And what I do is I apply what's called a monomap to that. So I flip the bits. So instead of 0, 1, 1, I now have 1, 1, 0, which should be 6. So if I map that down here, I get 6. So the mapping between these 2 geometries is just given by this monomap, which is taking the bits of the site numbers and just reversing it. The point here is that once I've rearranged them and I've applied this tree structure, it actually looks like 0 and 4 are really close to each other now, which makes sense because they're connected by an interaction. And likewise, 0 and 2 are sort of close to each other, but not as close, and that's because they're connected by one of these weaker interactions right here. But let me make this a bit more explicit. So this is all very abstract, but what we can do in these systems is we can just let a particle run loose in the system. And what particles tend to do, especially in local systems, is they tend to just ballistically diffuse through the system. And so if we're interested in getting at the underlying geometry of the reals, well, maybe we just put a particle here and let it kind of ballistically diffuse its way along. And then if what I claim is true, that this new geometry leads to some, or this different coupling leads to some new geometry, then again, I should be able to let a particle here, and it will just sort of ballistically diffuse along. And that's what I'm going to show you next. So we've done some numerical simulations on this, and just as I said earlier, if I drop a particle here and let it do its thing under the dynamics of this system, we see this nice Lee-Robinson light cone. This particle is just smoothly diffusing. And what this is telling us is that I should think of this as a linear spin chain. No surprise. So here, and here's a great cartoon picture of this particle sort of spreading through the system. Now, by contrast, let's go to the other edge of this limit. So let's go to this furthest neighbor geometry. And if I put a particle down here and let it do its thing, it goes all over the place. It's a mess. It's a fractal pattern. But what I can do now is I apply this monomap, and I transform to my new geometry. And what we see is actually we recover a new linear light cone. So this particle is now smoothly, ballistically spreading through the system after I've transformed to the new geometry. So this directly tells us that there's something that has changed fundamentally about the underlying geometry, or the low energy physics of this model. This is still really early days for this. There's a ton still to be explored here, but I find this to be a very intriguing model that deserves further study. And moreover, we can implement models like these in the lab because we can do these different, changing the interaction strengths relative to one another. Okay, so I've just presented a lot in the last little section, but the star of the show here is this power of two model. And to review, this guy has the non-local interactions and chaos that we need for fast scrambling. It also looks like we can implement it in the lab, which is really cool. And then I introduced this new exciting feature, which is this emergent geometry. So it looks like we actually have a candidate for fast scrambling. And I'd just like to end with some final conclusions and thoughts about where to go, where to look next. So what I told you today was that optical cavities provide two ingredients for fast scrambling, the two necessary ingredients for fast scrambling, non-local interactions and chaos. I also showed you some evidence that we can actually do these non-local interactions in the laboratory. So I showed you some evidence of non-local spin exchange, and I showed you that we have the capability of locally imaging the system using an objective underneath the atomic ensemble. And therefore, what we can do is we have this really interesting non-locally interacting system, but we can locally probe it and see where information is spread. And then finally, what I showed you was the sparse interaction graph and showed you that, well, probably this will let us build a fast scrambler in the lab, probably. And then I also showed you this really cool new feature that shows some emergent geometry underneath the spin model. Okay, so that's really cool. I have a lot of stuff that I'm really excited about doing next. And while I'm excited, first of all, for the cavity lab, I will be leaving the cavity lab soon, but these guys are just getting started. There's a ton of stuff that they're doing right now. So the current efforts right now are focused on both doing these programming interactions, so building these exotic spin models with these relative intensity changes. And in addition, they're looking at tunable non-local XXE spin models. So I didn't really discuss this, but this has to do with this interesting integral model here. And in the meantime, they've been working on a bunch of technical upgrades, including putting individual sites in the system. And in addition, we're working towards eventually having smaller, older atomic ensembles. And this is one thing that I'm really excited about for the future, because I'm really interested in this phase diagram that I showed you earlier. The thing that we need in order to explore this phase diagram is we need to be able to tune the spin size. And remember that I mentioned that in these lattice sites, you can either have, we typically have about 100 atoms per lattice site. But if you get rid of some of those atoms, you can go all the way down to spin 1/2, or up to spin 1, spin 2, spin 3, etc. And that's exactly what you need in order to explore this left side of the stuff. So that would be a really cool thing to see in future experiments. Another thing that I'm looking forward to seeing eventually is the observation of this interesting emergent geometry, this emergent tunable geometry. That would be really cool to see. And for instance, creating local spin excitations in the system and watching them spread. That would be really fascinating. And then finally, if we can actually implement this power of two model and see a fast scrambling, build a fast scrambler in the lab. Obviously, that would be extremely exciting. And then in the long view, maybe we can build a black hole in the lab. I'm not claiming we can, but that would be a really cool thing to see. So from the theory side, I mentioned that there are these two ingredients for fast scrambling. It turns out that so these are actually necessary ingredients, but they're not necessarily sufficient. So it could be, I don't think this is known yet, but it could be that you have both chaos and non-local interactions, and yet you still don't get fast scrambling. And I'm interested in pursuing to what extent that's true or not. So what, the conjecture here is that if you have chaos and non-locality, then you automatically get a fast scrambler. That's not known yet. In addition, the bounds I talked about early on were spreading, information spreading, but they were at infinite temperature. So this means the system can really access any energy eigenstates it wants to. And it's interesting to consider how these bounds get modified at finite temperature, where we only have access to low energy eigenstates. And then again, I'm going to throw up this picture of this integral model. This is a case where a lot is not understood, and it'd be great to pursue that further. And then finally, the thing I'm the most excited about here is this power of 2 model for geometry. So for instance, one thing that differs, that this model has that differs from other similar fast scrambling models is that this actually has deterministic couplings. So a lot of models, if you are familiar with the Sachdev-Tayev model, have random disorder couplings. This guy's couplings are actually all deterministic. And so you can ask, what kinds of entanglement patterns are you going to get? And if a fast scrambler is known as a really fast encoder, what kinds of information is being encoded by that? Another question you can ask here is I presented these tunable geometries from a nearest neighbor to a furthest neighbor. We suspect that that tunable geometry is actually a quantum phase transition, so we nice to actually establish that. In particular, at this crossover region where all of the couplings are equal, is it a CFT? Can we solve it using large N techniques, etc.? So there's just a lot to be studied in this model. So that's my thesis defense. Thank you guys very much.
Protocol now is questions from the audience. We're allowed to give them a hard time. Come on, somebody wants to have it. Yes, back there.
So like you said, multi-locality, you can create disorder in the couplings. I was wondering, what's the general effect of disorder on the scrambling? I imagine that disorder might help you, so assuming you don't have the disorder in the coupling is help you with your.
It's actually really unclear. So in one sense, yes, it helps you in the sense that it encourages chaos. And one way to think of it is that if things are too ordered, so one way I like to think about these dynamics is if you can use what's called a Trotter decomposition of your Hamiltonian, and you can think about it as like applying little 2-qubit gates as the operator is spreading. If that process is too ordered, what can actually happen is you sort of undo some entanglement, right? You're trying to build up entanglement, but by applying some operators, you're actually accidentally undoing. Right? So if things are disordered, that actually tends to be suppressed. So in some cases, it tends to actually accelerate the process of fast scrambling. But I think your question is a very good one, and I think it's an open question of exactly what role disorder plays. Yeah. And another thing to say about that is that in this model, again, this power of 2 coupling graph, it does not have any disorder, and yet it still scrambles. So I think it's still kind of unknown. Thanks. So.
Question from your brother.
Oh, okay.
Way too. He says, why powers of 2? Could a similar model work for other primes?
That's a fantastic
Fantastic question, Bentsen.
Yes, indeed. I don't see why it needs to be a power of 2. It could be 3 or 5 or 7. I don't think that you would get any. Well, so okay, one thing that we've chosen, especially in this model, if you noticed, is that we are working. I worked in the slides with 8 sites, but we always choose them to be a power of 2, because otherwise you get this 7 sites and a couple. Maybe just go to the board. Well, maybe this is good. you start getting coupling patterns that just run all the way around, and they don't
Not
form these
regular.
closed rings. Yeah, so this has to do with the prime numbers. But so long as you choose, I think if you were to choose your graph size to be the power of whatever prime number you want, then I think that would be, you basically see this in physics.
Joint paper with the brother.
That would be awesome.
There was another question around there someplace. No? No one there, yeah.
I have a slight confusion. How do you define the speed of information spread?
So it's all defined by the commutators, these commutators that I introduced in the beginning. So what I do is I introduce an operator on one site, and an operator on another site, and I let one operator evolve in time. And that spreads out, and eventually they fail. So that's a really sharp. But I feel like I'm not understanding your question.
But my question is, say you have built this flat.
Yeah.
And if I ask you, okay, how fast does the information spread in this flat? How would you tell me the speed, sort of like the speed of light in this flat?
So you're getting more at like Lee Robinson bounds.
Sure, yeah.
Right.
Like there's a C in that expression. So
Yes, exactly. That's a great question. So that's what these, we'll just go back to my. Here we go. So this formula down here is a Lee Robinson bound that we proved with Yingfei and Andy, and in particular, this tells you what you need to know. So if you give me a black hole sort of system with some interesting connections, maybe it's all to all, I can immediately put a bound on how quickly information can there. And so you can think of this almost like telling you what the underlying geometry is, and you can interpret this in terms of some linear Lee Robinson fusion, but where instead of it being ballistic transport on some linear chain, it's ballistic transport on some.
I guess in your model, what is the relative speed in the model?
Oh, sorry, that's a great question. So that's determined by the normalization of the Hamiltonian. So that's just like the typical energy scale of the system.
And your little c is explicit.
Yeah. Sorry, so this is not the speed of light c.
Yeah, okay.
Yeah. So if yeah, it's just, you should think of this just as the norm of the Hamiltonian, which means that basically if I crank up the size of the Hamiltonian, things will happen faster. So I feel like I still haven't answered your question. But
Well, we can-
Yeah.
okay.
One more. Yes, sir.
I was wondering, since, this has to kind of do with information transfer across a graph, does this have relevance to neuroscience or, advanced machine learning?
I think it absolutely does. Yeah. I honestly, I don't know how. Honestly, you should talk to Ben about this. He's the expert in sort of more neuromorphic types of things. My guess is that absolutely it could be used for something like that, but I haven't thought deeply about it. So, yeah.
Can you help me, the concept of the graph diameter, how does that get scaled by the size of the optical cavity? The photons going back and forth, you go back and forth between this construction where it's physical distances between spin states versus this idea that the photons get to go back and forth from the cavity before they're locked down. How do I think of that in
I see.
the context of
Yeah.
this experience?
So yeah, probably what I should have done is say that, so our atoms in a very simple cartoon picture, they're all arranged in a line. They're really just in a chain physically. And so in most normal physical systems, atoms arranged in a chain would typically only interact with numerous numbers. And the point here is that this atom way over here can interact with this guy.
Because of the cavity.
Because of the cavity. And then what I'm doing in my mind is just taking these guys and making a circle out of them and drawing all the interactions between them. Okay. And so the all-to-all interactions, that's really just an abstraction. Does that answer your question?
Yeah, almost. What is D then?
Oh, what is D then? So D depends just on, well, in fact, in the all-to-all, it's just one. It's always one in the case of an all-to-all interacting pair. Because any particular atom can, how many hops does it take to get from one atom to any other?
So it's not a physical
Just one.
distance.
No, it's not a physical distance. Yeah. That's actually getting at kind of the heart of what's going on here. We're trying to like ignore real distances and we're trying to like make our own. Yeah.
So we're trying to engineer these exotic geometries. You know, really, we have an actual physical geometry that's sort of underlying it, which is going to be manifested via multi.
Manifested by what?
Well, some sort of interactions between atoms. Just local interactions, for example, collisions. Is that something you're limited by?
Yeah, that's a great point. So some things to say are, suppose, let's just start from the ideal case where I actually have one atom loaded into each lattice site. This lattice is really, really deep. In that case, the positional motion and degrees of freedom are just, they're just locked in. They don't go anywhere. And so in that case, no, there's no collisional physics going on. It's just spin interactions. Now, that's the ideal situation, and it's not really what's going on because we have hundreds of atoms per site. And so really they are colliding with each other and doing interesting things. The thing is though, on the time scales of our experiment, we can really think of them as just being crunched. So the collision time scales are much slower. So we really should think of these guys, yes, they're all colliding with each other, but as soon as we turn on the dynamics, you know, they all freeze. And they're doing some spin interactions. It's a great question. Yeah.
I was wondering what limits, like why do you have hundreds of atoms as well?
Yeah, that's a good question. That has to do with a combination of temperature and also convenience. So for us, a lot of the interactions are actually, they're aided by having many atoms. So you get this collective effect. It's, instead of I mentioned here that we have a cooperativity of 7.5, that gets bumped up to a collective cooperativity of 7.5 times 10 to the 5. And so having, or at least however many atoms you have. So having more atoms per lattice site actually helps us to see the dynamics. It helps it occur faster. So for the moment, that's actually a convenient feature of a bug. And actually, that's the trickiest thing if we want to lower the number of atoms per lattice site, is that things would slow down because we lose this collective effect.
Because they interact with each other within each lattice site, or
No, the right way to think of it is that imagine in each lattice site I have a big spin where the size of the spin is given by like the number of atoms divided by 2. This big spin, the rate at which it interacts with other spins contains a factor of that S. So I'm going to get interactions that happen faster because of larger spin sizes. If I reduce that, then everything kind of slows down. We start to lose to dissipation instead.
Might be reasonable, given that there's more to go for him and for some of the rest of us, if we thank him for a wonderful talk.
Thanks for coming, guys. I appreciate it.
It was a great talk. 5 minutes. Go run around the block.
Great.
Great.
From here. Hey, thanks for watching, everybody. Are we still live?
We're still live. There are 6
Appreciate
people. There are 6 people. Yes.
Jeff's one, we don't know. Is this on YouTube?
Yeah.
Anybody can see it?
Anybody
Only
with
with
the link. Right now, it's anybody with the link.
Yeah, okay.
Yeah.
And 5 other people? Oh, so yeah, so but you'll also have it for. Yeah, you should definitely.
Yeah. And we've got to also record it here, so
No questions.
got a backup. All right. Bye, you two.
Yeah, I can do it. Go over that again.